In this lesson, we will examine prime numbers. Now, prime numbers can be thought of as the building blocks of all integers. As such, you must fully understand the nature of prime numbers in order to successfully tackle questions related to integer properties. Okay, so what exactly is a prime number? A prime number is any positive integer that has exactly two positive divisors. So here are the prime numbers up to 59. Be sure to memorize these. Now, while there is an infinite number of prime numbers, it is very unlikely that you will ever need to know any primes greater than 59. Okay, let's take a closer look at some prime numbers. 2 is a prime number since the positive divisors of 2 are 1 and itself. Similarly, 17 is a prime number since its positive divisors are 1 and itself. So the two divisors of any prime number will always be 1 and the number itself. Conversely, 39 is not a prime number since 39 has 4 positive divisors and prime numbers have only 2 positive divisors. Now, when it comes to prime numbers, you should be aware of two important points. First, 1 is not a prime number. It is not a prime number because 1 has only 1 positive divisor, and prime numbers have exactly 2 positive divisors. The next point is that 2 is the only even prime number. Every other prime number is odd. You will find that there are many questions that test this last point. Okay, so that's the deal with prime numbers. In the next lesson, we'll examine how prime numbers are the building blocks of all integers. In the last lesson, we examined prime numbers. During that lesson, I suggested that prime numbers are the building blocks of all integers. Now, the meaning of that statement is best illustrated by the following theorem. It says that any integer greater than 2 is either prime or can be expressed as the product of prime numbers. So, for example, 21 can be expressed as 3 times 7, where 3 and 7 are both prime numbers. We call this the prime factorization of 21. Similarly, 60 can be written as 2 times 2 times 3 times 5, where all of the numbers are prime. This, incidentally, can be written as follows. Now here's the prime factorization of 250, and here's the prime factorization of 7,644. An important point about the prime factorization of a number is that it is unique. For example, this is the only way to express 7,644 as the product of prime numbers. As you will see later in this lesson, we can learn a lot about a number by examining its prime factorization. So we need to become proficient at expressing numbers as the product of prime numbers. I'm going to show you one technique for doing this. Let's say we want to find the prime factorization of 60. Now, 60 is not a prime number, which means we can write 60 as the product of two numbers. What are two numbers that multiply to be 60? Well, one pair of numbers is 6 and 10. Let's examine these two numbers. First, we have 6. Is 6 a prime number? 6 is not prime, which means we can write 6 as the product of two numbers. Two numbers that multiply to be 6 are 2 and 3. Both of these numbers are prime, so we'll circle them to remind us that we can't factor these two numbers any further. Now, what about 10? Is 10 prime? 10 is not prime, so we can write 10 as the product of two numbers. Two numbers that multiply to be 10 are 2 and 5. 2 and 5 are both prime, so we'll circle them. We have now broken 60 down into several prime numbers. So 60 will equal the product of the prime numbers found at the ends of the tree. We can write this as follows. Now, this technique can be applied in several different ways, and it will always yield the same prime factorization. To demonstrate this, let's find the prime factorization of 60 again. Once again, we know that 60 is not prime, so we want two numbers that multiply to be 60. This time we'll use 3 and 20. When we examine these two numbers, we see that 3 is prime, so we'll circle it. Now 20 is not prime, which means we can write 20 as the product of two numbers. It doesn't matter what two numbers we use, just as long as they multiply to be 20. How about 10 and 2? Now 10 is not prime, so we'll leave that for the moment. 2, however, is prime, so we'll circle it to remind us that we can't factor this number any further. Now 10 is not prime, so we can rewrite it as the product of two numbers. Two numbers that multiply to be 10 are 2 and 5. 2 and 5 are both prime, so we'll circle them. We've now reached the ends of our branches. At this point, we can see that 60 equals the product of the numbers at the ends of the branches, which we can rewrite as follows. Notice that this product is the same as the product we got from the first attempt. Now, finding the prime factorization of a number is a very useful technique, so be sure to practice it on several large numbers. At this point, you might be wondering how prime factorization is supposed to help us tackle integer property questions. Well, the prime factorization of a number tells us a lot about that number's divisors. Here's what I mean. Let's say that we know the prime factorization of 1540. From this, we can see that 2 must be a divisor of 1540. We know this because in the prime factorization of 1540, we have a 2. This tells us that 1540 is equal to 2 times some number, which means 2 must be a divisor. Similarly, we can see that 7 is a divisor of 1540, and 11 is a divisor as well. Also from the prime factorization, we should see that 4 is a divisor of 1540. Now, there might not be an actual 4 in the prime factorization, but if we recognize that 4 is equal to 2 times 2, then we can see that there is a 4 hiding as 2 times 2. Similarly, we can see that 77 is a divisor of 1540. This is because 77 is hiding within the prime factorization as 7 times 11. Finally, we can see that 110 is a divisor of 1540. This is because 110 is hiding within the prime factorization as 2 times 5 times 11. Using the prime factorization, we can also see that 3 is not a divisor of 1540, since there is no 3 to be found in the prime factorization of this number. Similarly, 8 is not a divisor of 1540. We know this because 8 is equal to the product of 3 2's. So for 8 to be a divisor of 1540, there would need to be 3 2's hiding within the prime factorization. Since the prime factorization has only 2 2's, we know that 8 is not a divisor. One last example. 33 is not a divisor of 1540, since 33 is equal to 3 times 11, and the prime factorization of 1540 does not include a 3 and an 11. Now, in an earlier lesson, we saw that there are several different ways to say that one number is divisible by another number. We'll now add another line to this list. If x is divisible by y, it must be the case that y is hiding somewhere within the prime factorization of x. So, for example, if we are told that 6 is a divisor of w, we know that the prime factorization of w must have a 6 hiding somewhere. Now, since we're talking about the prime factorization of w, the 6 will be hiding in the form 2 times 3. Similarly, if we are told that r is divisible by 88, then we can conclude that there must be an 88 hiding somewhere within the prime factorization of r. Of course, that 88 will be hiding in the form 2 times 2 times 2 times 11, since this is the prime factorization of 88. So, to summarize, the prime factorization of each number is unique. The prime factorization of a number can help us determine its divisors, and if some number k is hiding in the prime factorization of a number, then k must be a divisor of that number. In a previous lesson, we found the number of positive divisors of small numbers, and we did this by listing the divisors. But what if we want to find the number of positive divisors of a large number, such as 14,000? In this lesson, we will examine a technique for this. Now before we continue, I should tell you that it is not necessary to know why this technique works, but I'm going to show you anyway. For some students, the rationale behind this technique may be useful when tackling advanced integer properties questions. Okay, to begin, please recall something we learned in an earlier lesson. Now here we have the prime factorization of 720, which incidentally we can write as follows. Given the prime factorization of 720, we can draw several conclusions about the divisors of 720. For example, 4 is a divisor of 720, since 4 is equal to 2 times 2, and in the prime factorization of 720, we have 2 times 2. Similarly, 18 is a divisor of 720, since 18 equals 2 times 3 times 3, and in the prime factorization of 720, we have 2 times 3 times 3. Finally, 40 is a divisor of 720, since 40 equals 2 times 2 times 2 times 5, and this same product can be found in the prime factorization of 720. Now here comes a very important observation. Since the prime factorization of 720 consists solely of 2's, 3's, and 5's, the divisors of 720 must be in the form 2 to the power of a times 3 to the power of b times 5 to the power of c. Now since the prime factorization of 720 has 4 2's, a can be any number from 0 to 4. Since the prime factorization of 720 has 2 3's, b can equal 0, 1, or 2. And since the prime factorization of 720 has 1 5, c can be either 0 or 1. We're now going to use this information to determine the total number of positive divisors of 720. We will do this using some counting techniques you may have not seen before. We're going to build divisors in stages. Since all divisors will be in the form 2 to the power of a times 3 to the power of b times 5 to the power of c, our first stage will be to select a power of 2. Our next stage will be to select a power of 3, and our last stage will be to select a power of 5. Beginning with the first stage, the power of 2 can be 0, 1, 2, 3, or 4, so there are 5 ways to accomplish this stage. On to the next stage. The power of 3 can be 0, 1, or 2, so there are 3 ways to accomplish this stage. And finally, the power of 5 can be either 0 or 1, so there are 2 ways to accomplish this stage. Applying the fundamental counting principle, we multiply the number of ways to accomplish each stage to see that there are 30 ways to accomplish all 3 stages. So, 720 has 30 positive divisors. Now before we generalize these results, notice that the number of ways to select a power of 2 is 1 more than the exponent of 2 in the prime factorization of 720. Similarly, the number of ways to select a power of 3 is 1 more than the exponent of 3 in the prime factorization of 720. And finally, the number of ways to select a power of 5 is 1 more than the exponent of 5 in the prime factorization of 720, since the exponent here is 1. Okay, now let's generalize. If n is equal to p to the power of a times q to the power of b times r to the power of c and so on, where p, q, r, and so on are prime numbers, then the total number of positive divisors of n is equal to a plus 1 times b plus 1 times c plus 1 and so on. Notice that this technique requires us to find the prime factorization of the target number. So now let's apply this technique to find the number of positive divisors of 14,000. So first we will find the prime factorization of 14,000. And now to find the total number of positive divisors, we will take all of the exponents here and increase each of them by 1 before finding their product. When we evaluate this, we get 40, so 14,000 has 40 positive divisors. And that is how you calculate how many positive divisors a number has. If you wish to practice this technique, you can confirm the following.